Okay, hello guys. So let me make sure I get this one. No. Okay, so we're gonna start with abstract algebra. So I guess I wanna give you a motivation first. And this is a very famous example. And so I think everybody has played a Rubik cube, right? And turns out that the permutations, like of this Rubik's cube for a group, a fundamental concept within abstract algebra. And indeed, that's the topic of today. We're going to define what is a group. So all these permutations for a group, and we're going to define it. But abstract algebra is a very important concept. Is you probably have heard about the Fermat theorem. So Fermat theorem. Fermat's theorem that was proved like 25 years ago, something like that. And and sorry, let me see it. So let me find it again. Fermat theorem. This one. So so basically, it's saying there are no solutions for a to the n plus b to the n equals c to the n, right? For n bigger, that's certain number, right? So for any value n greater than 2, because we know this is Pythagoras, right? A squared plus b squared equals c squared. We have solutions that are the triangles, okay? But it turns out that there are no solutions for n greater than 2, okay? That took 300 years to prove. And the proof, between other things, use all these concepts of abstract algebra. They use rings, ideals, Galois theory. So this is a long, is that like real analysis is one thing, abstract algebra is another big thing. So this is a very common topic in the PhD. Okay, so that's a very common topic for a qualifier. Okay, so we're gonna start, and I'm gonna give some ideas. So we're gonna follow the book by and it's already available in announcements. Thomas Judson from Stephen Austin State University. Okay, so this is a good book. I want to do, before jumping to that, there's some good theory behind of that. But yeah, well, so we did some previews in the first week. We did a previews of congruences. Okay, so remember, so let's start here. Abstract algebra. abstract algebra, right? So recall we used to say that two integers a and b are congruent or equivalent modulo n if only if n divides a minus b, meaning you want if and only if there exists k integer. So let's select a, b integers. There exists k integers such that n divides a minus b, so a minus b equals k times a, n. Okay? So that's something we did, and we're gonna do some review of that, okay? So what is gonna happen is that we are going to consider, for example, we can say C12. Okay, so what is C12? So C12 is gonna be the set of the 0 class, the 1 class, the 2 class, all until 11 class. Okay? So all the integers, you're going to divide the integers in 11 groups, or 12 groups, 12 groups. And 0 is going to be 0, 12, 14, 24, 36, and so on, minus 12, minus 14, and so on. So basically, 0 and 12 is the same thing in this class. 0 and 12 is the same. Then we have the 1 class, and then for 1 class you have 1, 13, minus 11, 25, etc. Then you go all this way, and this is 11. That's 11 minus 1, 23, 35, and so on. Okay? So, for example, what is 14? Okay? So for this, you need to divide 14. Let me check. I always make this notation wrong. Let me check the notation. So, okay, let's do, well, let's do, for some reason, I always like to do this one. Let's say 21. What is 21 modulo 12? Okay, this is equals to, or is congruent to what? So what we need to do is make the division in 21, and then we divide by 12. So I need to check because in my country, the way that we do the division is a little bit different. The notation is the same thing, but just the notation is a little bit different. So this is, what do you have? 1 times 12 is minus 12. And then this is 9, right? 21 minus 9, 12 is 9. So the residue is what you need. So this is 21 modulo 12 is 9. It's congruent to 9, no? Right? And you write it like this. So 21 equals is 1 times 12 plus 9. And this is going to be a very important theorem that is called the division algorithm. Okay, so let me write it down. The division algorithm. So let me tell you that there are going to be some final presentations. And this is going to be one of them. So I'm going to give you a lot of time to prepare, but you need to prove the division algorithm and you need to record it and upload it in Blackboard. Okay. So division algorithm. So let A and B be integers with B bigger than 0, then there exists unique integers Q and R such that A equals B times Q plus R, where R is between 0 and B. Okay? That's what we're using here, you see? This doesn't show in the theorem, division algorithm theorem. This is what it shows on the theorem. This is a way kind of to prove. Okay, so we will do this several times, and we do several times this over here. So this is kind of not what we usually do, but this is what we do every time over here. But this is what in people in astrology call the division algorithm. Okay. Okay, so we have the division algorithm. The other one that I'm gonna ask you to prove as a final presentation is fundamental theorem of arithmetic. Okay. We're gonna have those. Okay. Okay, so thanks to the division algorithm, we can construct these guys. Okay. So you can construct Cn. Okay. So those guys need arithmetic. Okay. So we need to define, we're going to define the sum for those guys. So that's going to be a group. It's going to be a set with an operation satisfying some properties. Okay. So we're going to, for example, do like what is 7 plus 4 congruent on module 5. Okay. What is 3 plus 5 congruent module 8? What is 3 plus 4 congruent module 12? What is 7 times 3? So you can also put multiplication. Okay. But for group theory, you just need one operation to start with. Well, we will see. We'll see. Let me not go ahead. So then you have 7 times 3 is congruent to mole 5 something. 3 times 5 is congruent to something mole 8. And 3 times 4 is congruent to something mole 12. Okay. So you guys tell me. So what is 7 plus 4 module 5? So you need to do 7 plus 4 is 11, module 5. You do your division algorithm in your head, and the answer is 10 plus 4 is 11. So you divide by 5. So 11 divided by 5. 2 times 5 is 10 minus 10. 1. The answer should be 1, right? 3 plus 5 is 8. Module 8 should be 0. 3 plus 4 is 7. Module 12, 7. 7 times 3 is 21. Module 5 should be 1. 3 times 5 is 15. Module 8 should be 7. 3 times 4 is 12. Module 12 is 0. Okay. So I did those. Let me check the book. Yeah, everything is good. Did you see you do those counting in your head? Okay. So then we have that we can have kind of a table. Okay, we can make so this space. So example. So we're going to study C8. Okay. So what is C8? So we're going to do June, June. And we take the representative. So we said 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And we are going to do multiplication. So this is going to be CA with multiplication. Oh, I missed the 0. Sorry. I missed the 0 here. 1, 2, 2. 0, 0, and 0. 0 times 0 is 0, 0 times 1 is 0, 0 times 2 is 0, 0 times 3 is 0, 0 times 4 is 0, 0 times 5 is 0, 0 times 6 is 0, 0 times 7 is 0, right? Now 1. 1 times 0 is 0, 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, 1 times 5 is 5, 1 times 6 is 6, 1 times 7 is 7. Now 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. Module 8, that's 0. 2 times 5 is 10. Module 8, I get 2. 2 times 6 is 12. Module 8, I get 4. 2 times 7 is 14. Module 8, I got 6. So we can go in 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. Module 8 is 1. 3 times 4 is 12. Module 8 is 4. 3 times 5 is 15. Module 8 is 7. 3 times 6 is 18. Module 8 is 2. 3 times 7 is 21. Module 8 and 5. Yeah, 5. Right. So 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8, that is 0 here. 4 times 3 is 12, model 8 is 4, 4 times 4 is 16, model 8 is 0, 4 times 5 is 20, model 8 is 4, 4 times 6 is 24, model 8 should be 0, 4 times 7 is 28, model 8 should be 4. Okay, I'm going fast, so let me check. 4 0 4 0 4 0 4 0 4 0 4 0 3 6 1 4 7 2 5. Yeah, so far I'm good. So you guys let me know. 5 times 0 is 0, 5 times 1 is 5, 5 times 2 is 10, module A is 2, 5 times 3 is 15, module A is 7, 5 times 4 is 20, module 8 is 4, 5 times 5 is 25, module A is 1, 5 times 6 is 30, module A, so is what? 6. Yeah. 5 times 7 is 35, module A is 3. 6 times 0 is 0, 6 times 1 is 6, 6 times 12, module A is 4, 6 times 3 is 18, module 4 is 2, 6 times 4 is 24, module A is 0, 6 times 5 is 30, module 8 is 6, 6 times 6 is 36, module 8 should be 4, 6 times 7 is 42, so module 8 should be 2, 0642, 0642, yeah. And then the last one is 0 times 0 is 7 times 0 is 0, 7 times 1 is 7, 7 times 2 is 14, module 8 is 6, 7 times 3 is 21, module 8 is 5, 7 times 4 is 28, module 8 should be 4, 7 times 5 is 35, module 8 is 3, 7 times 6 is 42, module 8 is 2, 7 times 7 is 49, module 8 should be 1. 6 times 8, 44, 48, right? So 7, 6, 5, 4, 3, 2, 1. Okay. And this is kind of my multiplication table. Multiplication table for C8. Okay. Okay, so so I think with that, so let me pause here, this pause, and then we're gonna continue with a proposition, and then give now examples of. So this is gonna be examples of groups. Okay, this is I'm kind of building. And then we're gonna have, next thing, we're gonna have permutations. I haven't even defined you what is a group, okay? But probably soon I'm gonna do that. I just wanna introduce you the different kind of sets that we are gonna work with. I don't wanna say spaces, but like where are we gonna move? What kind of examples we're gonna use? Okay, I'm gonna be showing all the time.